Welcome to a tutorial on the 8255A BSR mode programming. Alright, now BSR basically stands for bit set reset, okay? And when you're operating the 8255A chip in the BSR mode, then what you do is that, well, you can basically configure the port C, okay? So as an output port, okay? So you can basically configure port C as an output port, okay? And the speciality of this particular mode of 8255A chip is that when you're configuring port C as an output port, you can control individual lines, okay? So this way you just set up a control word. So basically set up corresponding control word, okay? And by doing that, you can basically control, okay, each bit or each line of port C. So you can basically either set or reset, okay, each line of the port C. Alright, so let's say you wanted to set the line, let's say C0, okay, then you can do that by just setting up the corresponding control word. Even if you wanted to reset it later, then just give the corresponding control word and you get your job done, okay? So now in this tutorial, we're basically gonna focus our attention on setting up the control word for setting each and every line, or rather just set up and reset a particular line of port C while operating in the BSR mode. And we're also going to learn how to write a program for doing that, okay? So first up, we're basically gonna lay stress over here. We're setting up the corresponding control word, how to do that. Now we had seen in the previous tutorial that, well, the bit D7, okay, of the control register is what actually controls whether the chip should operate in the BSR mode or in the normal input-output mode. So by putting D7th bit of the control register word, okay, to logic 0 level, we can set the 8255A chip in the BSR mode. Alright, so if this yellow box over here represents our control register, okay, then in that case we know that we need to keep the bit D7 here set to logic 0 level so that we can access the chips, the 8255A chips BSR mode. And now let me tell you that the bits D6 through to D4 are of no importance over here, but they are not used, okay? And so you can just regard them as don't care states. And here, well, we need to give an 8-bit control word. So what do we do in real situations? Well, what we do is that we generally, okay, these D6, D5th, and D4th bits are generally set to logic 0. Okay, so they're generally set to logic 0. So we provide a 0 for each of these bits over here. But the main bits of importance comes in the D3rd, D2nd, and D1st bits. So D3, D2, and D1 bits are here is what actually is important. Okay, so by putting a corresponding 8-bit, or rather more precisely, 3-bit code over here, we can access any of the lines of the port C. Okay, so I'm giving you an example over here. So if you just D3, D2, and D1, if you might just write it down over here, then if you just keep all of these bits at logic 0 levels, then we can access the C0 line of port C. Similarly, if we just keep them to 001, if we just set D3, D2 to 00, and D1 to a logic 1 level, then we can access, or rather select, the line C1. So in this way, by setting up the corresponding 3-bit code for each of D3, D2, and D1 positions, bit position that is, we can select the corresponding line of the control, of the port C over here. Okay, and lastly, the bit D0 of the control register while the chip is operating in the BSR mode is basically regarded as a set or reset bit over here. So if you're gonna put a logic 1 level at the bit D0, then you're basically setting the selected line, okay, whose code you provided at the D3, D2 and D1 bit positions respectively. And if you just set it to logic 0, then you're resetting the line. Okay, so let's just take up a problem statement over here. Okay, there we have. Now here's a problem statement which says, well, operate 8255A in the BSR mode and write a program to do the following. So we need to set the line C2 and C5. Okay, so we need to put these lines C2 and C5 of port C2 logic 1 level. Okay, and then what we need to do is reset C2 and C5 after 0.3 seconds. Okay, so we need to set up a delay of 0.3 seconds and keep the line C2 and C5 at the logic 1 level for 0.3 seconds and then reset them afterwards. So this is what our assignment is over here. So in order to do that, we need to set up the appropriate control word. Okay, so I've just drawn two boxes, one for the line C2, okay, and the other for the line C5. Okay, so now we need to set up their corresponding control words. So we know that in order to keep the chip in the BSR mode, we need to put the D7th bit, or rather set the D7 bit to logic 0. So we just put logic 0 for each. Okay, and then D6, D5, D4 are generally set to 0. So we just put 0, 0, 0 in each of them. So now the rest of the bits are of importance. So for C2, we need to select the line C2. So let's just check up the chart over here. In order to select C2, we need to give this particular 3-bit code, that is 0, 1, 0. So we put 0, 1, and 0 in the positions of D3, D2, and D1 respectively. And similarly, to select the line C5, okay, there we go, we need to provide the 3-bit code 101. So I put 1, 0, and 1 at the positions D3, D2, and D1 respectively. Okay, now we need to set each of them. So in order to set each of these lines, okay, that's to set these lines up in the logic 0 state, logic 1 state, sorry, we need to provide a logic 1 level at the D0 bit positions. So we just put 1 in each of them. Okay, so now that we have our 8-bit control words for each of the lines C2 and C5, their hex equivalent word, or rather hex equivalent value for that of C2 would be, well, if we just take the 4 bits each, then we're going to get a value of, well, 0, 5H, okay, for C2. And for that of C5, again, if we just divided the entire 8-bit code into, 8-bit control word into 4 bits each, then we're going to get about 0, B. Okay, so these are our corresponding hex control words for that of C2 and C5 respectively. So now we're basically gonna write the program. But just before going to the program, let me just remind you of this diagram which you came across in the previous tutorial. So this is the circuit that we just constructed in order to interface the 8085 microprocessor. I think you can see the name. Okay, that's better. So this is a circuit we use to interface the 8085 microprocessor with the 8255A chip. Okay, so we're going to use the same circuit over here as well to interface both the chips, and out of that we obtained this table, okay, from which we obtained the control register's output port address, okay, which is just 83H that we can see over here. So now we need to keep this in mind, that we need to access the control register, and over there we need to send these control words. Okay, so this is what you need to keep in mind. Alright, okay, so now we're on to our program. Alright, so now in order to set up these control words concerned, we need to, let's just start with the line C2 first. Okay, we're supposed to load this particular hex control word into the register A and then send it to the control register. Okay, so we're gonna do that by writing the codes. Well, MVI, okay, A comma, let's check up the code once again. Yeah, that's 05H for C2. So 05H. So as the comment says, 05H is basically the control word to set the line C2, and we're just loading it into the register A. Okay, and after that we're just gonna send it to the control register. So we are gonna write, well, out 83H. Okay, now in this case, as I described earlier, that by 83H is basically the port address of the control register, okay, and we're just sending this data stored in the accumulator, which is of course 05H, the control word to set the line C2. We're just sending it to the port of the control register. So this particular data, the 05H, is basically being transferred into the control register using this command. So we're gonna do the same for setting up the line C5 as well, but in this case the control word would basically be 0BH. okay, so back to our program once again. So there you go. So we have the same sort of statements. It is MVI for loading the data 0BH into the accumulator register, and then again sending it to the control register using its port address 83H. Okay, now with these statements executed, we find that the lines C2 and C5, they basically were both set to logic 1 levels, okay, and as an indication of the fact, if we would connect two LEDs over here, let's just call them, well, let's say D1, or rather as LED1. Okay, this is LED1 and this is LED2. okay, let's just call them that way respectively. So as an indication, if we would connect by two LEDs to the lines C2 and C5 correspondingly, they would just start to glow at this moment, because both lines C2 and C5 have been set to logic 1 levels. So this just lights up the LEDs D1 and D2. And now the problem statement says that we need to reset them after 0.3 seconds. So after setting them up, we need to provide a delay of 0.3 seconds. And for that, we need to call a delay subroutine. Okay, so we're gonna give the instruction of a call, okay, and then write a delay. Well, don't confuse this particular term delay as a command. Well, this is definitely not a command. This term delay is just the name of a particular level. You can see that in the program where we just divided it into several columns. So level is just one of them. So we just named the level where the delay subroutine program is stored. Okay, so we're just giving the name delay over here because we don't know where it is stored. Okay, so now I'm going to talk about a bit on the subroutines. Now a subroutine can basically be defined a part of the main program, okay, which is basically was stored in a different memory location, and it is just separated from the main program body. Okay, so if you would just take a look over here, that we have our main program. So this is our main program that we're writing here. Okay, so this is basically our main program, okay, that we're writing over here. So now this is actually the program body, the entire instruction set that this constitutes the main program. Okay, so this just forms the main program body. And now the delay program which we are gonna write here, well, is just separated from the main program body, and it's just kept in a different memory location. So we haven't talked about where to keep it, which we'll decide it later. But if we have a subroutine, then we basically use the statements or the commands call and return, okay, to work with them. So this particular statement, that is call, is used in the main program body. So this is just used in the main program, okay, to call or access a subroutine, to access or call a subroutine. So what happens is that when in case of constructing complex programs on very complicated systems and all, we need the program to perform a lot of functions and monitor a lot of things. Okay, so in that case, where the subroutine making capability of the 8085 microprocessor, well, it just makes it the life of a programmer, okay, a little easier in a way that, if you have let's say the program performing 5 different or 10 different functions, so you can just write a subroutine for each of the 10 different functions that you need your program to perform. So in that case, what happens is that for each subroutine would just be stored in a different memory location, and at whichever part of the program, like say for example in this part, okay, after we just send the control words to the control register, okay, and set up the lines C2 and C5 to logic 1 levels. Now we need to provide the time delay. So now we need the delay subroutine to generate a delay of zero point 0.3 seconds. So in that case, we're just calling the subroutine over there. So in the same way, whenever and wherever you require your program to perform that particular function, okay, and you have 10 different subroutines for 10 different functions, then you can just call the required subroutine at the particular time whenever you require it. So this is just a particular feature of the 8085 programming system that just makes it easier to work with complicated systems. So the statement call is the command call is just used in the main program body to call or access a subroutine, and the syntax goes somewhat this way. You're supposed to write a call and then provide the starting memory address, okay? So it's gonna be starting memory address, okay? So this is gonna be the starting memory address of the subroutine. Okay, so this is the point. Okay, so you just stored a subroutine in some different memory location, and if you just provide the starting memory address after call, so the program controller transfers into this particular part. Okay, now one thing I need to add over here, but that before encountering the call command over here, the program counter contained the memory location of this last out statement that we had executed here. Now immediately after encountering this call command, the program counter contains, okay, which just contains the memory location of this last out statement over here. It just gets stored into a stack, okay? So the program register is just the program counter register is just currently cleared off the main program main program's memory location, and it just was stored into a stack memory, okay, outside the 8085 chip. And at this particular time, the starting memory address of the subroutine will get loaded into the program counter register instead, and then the program execution will transfers to this particular memory address, and it just starts executing. And after the subroutine has executed itself and its function is done and over, then we have to write a statement, a command known as ret or return. So this just stands for a return. So this command, what it does is that it just returns the control back to the main program body. Okay, so it's just used in the subroutine to return to the main program as described over here. Okay, so now the syntax for the return statement is just pretty straightforward. You just after you just written down the corresponding codes of your subroutine. Okay, so let's say you just write down some codes of some lines of code for your subroutine, and then at the end, when you need the program to transfer, or rather the program control to transfer to the main program body, you just give ret. Okay, so at this moment the control returns from the subroutine to the main program, and at this point of time the program counter register is once again loaded with the address the address of the memory location of the main program body from where it left for accessing the subroutine. Okay, well, with that said, now you have an idea of what a subroutine is and why we need it. So we're gonna write the delay subroutine a little later, but let's just finish our main program body first. So now after we've just called the subroutine, and well, let's say we just imagine that we generated a delay of 0.3 seconds, and well, in this case I just forgot to add the comments. So there you go. You can just make your understanding a little bit easier. So after we just called the delay program and generated a 0.3 second delay, okay, we are supposed to reset the lines C2 and C5 once again. Okay. So in order to do that, we are supposed to go back to creating or finding out another control word for resetting the corresponding lines. So here we know that only the D0 bit just needs to be modified, because if you just put the D0 bit to a logic 0 level, then the corresponding lines, the voltage levels on the corresponding lines will just be reset. So we just rub them out, and well, we would need, you know, different values of hex data, okay, for the control words of the lines concerned. So we're gonna just put a 0 and the D0 bit positions. And now for C2 we're gonna have a different control word. It's gonna be what, 04H, okay, that's the hex value. And that for the line C5 it's gonna be, well, yeah, 0AH. Okay, so now we're just gonna set these control words up in the just load them in the accumulator register and then later send it to the control register for just resetting the corresponding lines. So let's go back once again, and we can see that in the circuit the LED 1 and 2 is still on at this moment, okay, because we haven't reset the lines. Okay, so we need to reset them now. So we're gonna load the accumulator once again. So MVIA comma, just check the code for C2, that is 04H. Okay, 04H, and there goes the comment. Okay, and then we're just supposed to send this control word to the control register. So we just write out, yeah, you're right, 83H. Okay, and we do the same for the line C5 as well. There you go. And well, after that, this just brings us to the end of our main program. So we just write the halt, or let's just write it over here, the halt statement. Okay, so this just marks the end of our main program. So this is the end of main program. Okay, and now, okay, so now we have just provided the hex codes and memory address for the main program that you can see over here. Okay, and now let's just imagine that our system has a memory range starting from 0000H to 3FFH. Okay, so this is the memory address range of our system. Okay, so in that case, let's just hope, or let's just take it for example that our subroutine program starts from the the memory location. Let's say take it as 2000H. Okay, so this is going to be the starting address of our memory location. So of the subroutine basically. So we're gonna put over here. Okay, we're just gonna rub this out, the delay. Okay, and we're gonna put the starting address of our subroutine memory location, that is 2000H. Okay, so this is the indicated by the level delay, okay, that was there previously. So now let's go to our subroutine program. So it's just gonna begin over here. Okay, so this is our subroutine delay program that we've just written over here with their corresponding hex codes and the memory addresses. Okay, so we can see that it's just beginning at the 2000H and was ending at 2007H. Okay, so I'm just going to explain what it does basically. So we are exploring the main concept of generating a time delay, okay, using a particular subroutine program. So what we do over here is that we just load the HL register pairs with a 16-bit number, which in this case is FFFFH. So FFFFH is basically the highest 16-bit number ever available. So we tried to make the time delay large enough to achieve 0.3 seconds. You see that whenever the 8085 microprocessor executes each of these instructions in the subroutine program, it just takes up a certain amount of delay, time delay for each of these instructions in order to execute them. Okay, so we've just thought of this principle over here and thought about using this property of the 8085 microprocessor to generate the time delay necessary. So in this case, what happens is that if we'd use a crystal of 6 megahertz frequency connected with the oscillator network, oscillator circuit of our 8085 microprocessor, then its clock frequency is gonna go down to 3 megahertz. It's gonna be 3 megahertz over here. So if the 8085 has a 3 megahertz clock frequency, then it'll basically have a clock period, okay, of approximately 0.33 microseconds. Okay, and this is just also referred to as 1 T state. Okay, so if I might write it in a bit clearer place, so here 1 T state, refers to that 1 clock period. Okay, so this is equivalent to 1 clock period. So in this case, with 3 megahertz of clock frequency, 1 clock period is approximately similar to or is equivalent to a 0.33 microseconds if you would just calculate it. All right, so here if you look at this chart, that each of these statements have been used in writing the subroutine program. Okay, so what we've done here is that, well, each of these statements would take this many T states. So like for example, the J and Z takes about 10 T states if its condition is true. If it encounters no zero condition, okay, and then jumps, then it just takes up 10 T states. Otherwise, if the condition goes false over here, then it just takes up 7 T states. So for convenience, we just thought about taking 10 T states for all, because these delays would just be very meager. And now each of these statements, they take up this many number of T states. So if we just for simplicity's sake, we'll just take it this way, that the J and Z statement takes 10 T states throughout. Then in that case, what happens here is that we're setting up a loop over here. Now you can see that about DCX and J and Z, they just set up the loop. Okay, so we load this 16-bit counter, okay, into the HL register pair, and then decrement the value of the HL register pair until it just goes down to, until the data in the HL register pair just becomes 0000H. Okay, so this just continues to happen until and unless the count just goes, the HL register content is continue to decrement by 1, okay, until and unless it just goes down to this value 0000H. Okay, so this is just performed by the DCX, and the jump on no zero statement, or the command over here. So this loop here actually goes through 65,535 steps, or this many number of times this particular loop here is executed. So on the other hand, the LXI and the return statements are just executed once. So for LXI and return statements, we get a total time delay of, they executing only once each. Okay, they just give us a total time delay of 3.3 microseconds each. So that's a total of 3.3 plus 3.3, that just makes about 6.6 microseconds of delay. They just LXI and return statements provide us, but the entire time delay provided by this loop is huge. Okay, it is just, let's just check up these states. Okay, T states, so these together, the J and Z and the DCX statements together have 16 T states. Okay, so which is equal to approximately 5.28 microseconds. Okay, and now this just keeps repeating for 65,535 times, which is just similar to the value hex value FFFFH. So if we would just multiply this figure with this many numbers, so 5.28 microseconds, okay, multiplied with this value, we're gonna get a total time delay of approximately 0.34 seconds. Okay, so we can achieve up to 0.34 seconds over here, which is, we can take it in approximately equal to 0.3 seconds. So here the criteria of the program that requires us to set the lines C2 and C5 at logic 1 state for 0.3 seconds is successfully made. And now let's just check the status of the lines concerned. Oh, they have just turned off. So LED 1 and LED 2 now have turned off because the logic levels here are at logic 0 levels basically, so they don't glow anymore. Okay, so with this example exhibited over here, we just come to the end of this tutorial, and we hope to meet you next in the forthcoming tutorials as well. So till then, just keep watching, and goodbye for now.